Nicole is a real soaring star in chemistry education research, and she's published widely on student reasoning and e-learning. She's also an associate editor of Chemistry Education Research and Practice. Nicole is, I suppose what you could call MISA royalty, having presented last year at MISA in Edinburgh. And today, Nicole is going to be sharing some thoughts on how we can go about challenging student intuition with item design. So very welcome, Nicole. I'll stop share and give it over to you.
Okay, is that working?
So we're just in, yep, that's it, yeah.
Okay, cool. Thank you very much, Ashton, for this nice introduction, and also Michael and Ashton for inviting me, because that's quite an honor for me also to contribute to this symposium or to this conference. And I greatly enjoyed being in Edinburgh last year. And yeah, so before we start, I want to say that I'm happy with taking pictures, and you can tweet. You can also follow us on Twitter. Here's my Twitter handle on the slide, or you can just have a look at our research group webpage. There you find there are mostly project description in English, but there are also some in German. Okay, so let's get started. Today, our leading question will be, how do people make decisions, and what does this actually mean for item design in chemistry education research? And this will be the roadmap for today, so the pre-reading, and I know not all of you had the time to actually look into that, is a paper that we published in 2019 with Renee and Sebastian. And Renee was an undergraduate research assistant in my group at that time, and Sebastian is a PhD student, and now they are both teaching in high school. And the first part of the talk will be on intuitive reasoning and how that impacts our everyday life, and as well students' decision-making in the chemistry classroom. Then the second part will be an exploratory study to challenge student surface reliance in organic chemistry, and what were our approaches and what were as well our struggles. And I know there are a lot of stats people here in the audience, so and I'm more qualitative, so we hope this will go well today. And then in the third part of the talk, I want to brainstorm with you where to go from there. So we'll talk a bit about continuing research ideas, and I hope that I can profit from the audience, and that you will profit as well from the conference in that part of the talk. Okay, so let's start with the quite general questions of how do people actually make decisions in everyday life. And I'm pretty sure that most of you know about this categorization into system 1 and system 2 thinking, but maybe there are also some people here in the audience that are not familiar with this, so I briefly go over that. Evans was one of the first to claim that human decision-making can be seen as guided by two different systems that can fulfill different roles and not always work together. The first system, thinking 1, is quite fast and intuitive, and it happens even if you're not aware of. And this is sometimes good because system 1 thinking helps you, for example, to catch a ball intuitively without calculating the speed and angle of the ball and adjusting your body to catch it. But it can also be bad if you really want to buy a car and it's maybe not in your budget. And besides this tricky intuitive reasoning, the system 1 reasoning or thinking, we are able also to use our knowledge and resources more consciously. And this is called system 2 thinking. And this is not effortlessly and requires a lot of cognitive effort. And both systems influence not only our everyday life, but as well how we learn and as well how we teach in chemistry. And sometimes, at least this is my impression, it's not that acknowledged in teaching and assessment. Because it's totally normal, and it's not surprising that students students will not stop thinking intuitively when sitting in the lecture hall. And we'll try how you are making decisions intuitively. And on the next slide, you'll see a simple question. And I want you to make a really, really fast judgment on that question and to hold on to this answer, even if you're tempted to change it, and until Michael has set up the poll. Okay, here we go.
So poll is live.
Okay, that's interesting. Okay, I think you can close it. Perfect. You see, most of you have decided to pick Frankfurt, and that's not surprising because Frankfurt sounds much more familiar to you than Essen. And some have used their system 2 thinking because they've chosen that the two cities are equally large. And the interesting thing is as well that Goldstein and Gigerenzer have used this question with international or American students and with German students. And one might think that German students would actually know much more about the size of these 2 cities and would be easily able to answer this question, but they did actually worse than the American ones. And how can that be possible? The Germans have too much knowledge about these 2 cities, and so they cannot rely on the familiarity, as both cities are pretty known in Germany. And so here the reliance on recognition that most of you in America or Australia could use fails for the German students. So sometimes one can conclude that knowing less can, and it depends on the question, be quite more effective than knowing more. So this is one, I would say, one positive effect of using heuristics sometimes. I will show you another example from another psychology study. Benoit Monin from Stanford investigated how we judge different faces when making decisions. For example, what would you say when somebody asks you to determine which of these 2 persons would you consider more friendly? And perhaps you already have a tendency. So most people would pick the person in A, although both pictures are not that different. Both faces have the same symmetry between eyes, nose, and mouth. And the picture in A just has an additional warm glow. And Monin could show that when people are making a decision here, they are attracted towards this warm glow of the picture, because this is associated with attractivity. And attractivity is additionally further associated with positive adjectives, such as being friendly or intelligent. And when we would answer this question with an analytical system 2 approach, we would have to conclude that we can't really make a decision here, as the relevant information is just missing. However, the fact that people answer this question shows that our intuition can sometimes be tricky and creates an illusion of competence in situations that are actually impossible to answer for us. And psychologists call this an attribute substitution effect, which means we intuitively tend to substitute a difficult, or in this case, even impossible question with one that is more accessible. And you may wonder what this has to do with organic chemistry and item design and so on. I will show you an example. So this is an item that I used in a former study to determine how students make their decision when answering those multiple choice items. And the prompt was to determine the appropriate reagents for the reaction. And the correct answer is circled, it's D. And many students in the study got the answer correctly, but the underlying reasoning was not what we would expect students to do. And the student, Hannah, she justified her decision in the following way. She said, I would go with D. There are 2 chlorines in the product, so with Cl2 and CH2Cl2, I guess you have enough chlorines to make it. So her approach to answer this question clearly shows this attribute substitution effect, and you may already have an idea what her question was. It was, where do I get the most chlorines from? So here you can see that although students are answering that correctly, their underlying reasoning was maybe totally different. And I also want to highlight some examples from the huge amount of literature that documents students' approaches when explaining and building arguments about chemical reactions. It comes from the Towns group. They looked at students' argumentation and found that, for example, these two reactions would be considered similar by the students based on how they look like, but not based on the underlying reactivity. The first reaction here proceeds through an SN1-E1 reaction. The alcohol is a weak base, and the second one has a good nucleophile and would rather proceed through an SN2 reaction. So here again, we see that surface features that students look at are more relevant for them to make their decisions. Mary Beth and Savina and Stacey Press looked as well at students' understanding of nucleophiles and electrophiles, and it's a great paper, so you should have a look into that. And they could see that although students are able to define what a nucleophile is, they were often guided by surface features such as charges or lone pairs to determine the presence of a nucleophile, instead of actually considering the function of a nucleophile in a reaction context. And here, our last example, this is from Talanka's studies on students' assumption and heuristic reasoning. It's been 10 years nearly since he published this, and it's still quite relevant. They looked at students' assumption when they determine acid strength, and they could observe that students were just kind of dissecting the molecule into different explicit features, and thereby also overlooking the interplay of these features for the respective property, for the acid strength that they had to judge or had to make a decision about. And this handful of study that I showed you right now is just a small selection of studies that document students' struggles to connect the surface features with the conceptual understanding. And this is a common theme in a lot of chem-ed research in chemistry, in organic chemistry. When you look at Bhattacharya's, Bodner's work, the immense amount of work that Allison and the Cooper group do, and I actually forgot some others to mention here. But to summarize the introduction, one can say that student success in organic chemistry depends largely on the ability to establish a connection between the chemical properties and the structural representation. Secondly, also to consider implicit properties of a molecule and just not be too much distracted by explicit features. And thirdly, when students move along their study program and their chemistry career, to determine which implicit property is actually relevant in a problem context, despite if there are distracting surface features. And this ability to make this connection and make a judgment in a problem context, we would call that relational conceptual understanding. And we were asking ourselves, how can we actually capture this ability to implicitly relate molecules and their properties together? And maybe that sounds a bit complicated right now. I'll show you how we went ahead to design items to capture this ability. So the item design was inspired by two theories. One is the variation theory of learning, and the other one is Dan Schwartz's work on learning through contrast. And I can highly recommend to at least look into the variation theory of learning when you're looking for theoretical frameworks. So the variation theory assumes that there are critical aspects of a phenomena that learner needs to simultaneously be aware of and focus on to experience that phenomena. Those critical aspects of a phenomena could be either explicit, so explicit features such as color or shape, or it could be implicit aspects. And some might be more salient than others, and so we have to take care about that in teaching. So then Schwartz investigated how we can use explicitly designed contrasting cases to support students to focus on deeper implicit commonalities instead of just looking at the similarity of surface features. So we try to combine objects that are conceptually related and as well similar on the surface. Now, while I was talking, you might wonder what the question is, as you have various possibilities to group these food items here on the slide. And we'll do a next poll here, and we will see how the audience is able to discern different features, implicit features of these displayed objects, and if they can show if you're able to think relationally. So here comes the question, and Michael will pull out the poll. Okay, I think everybody has made their choice. Okay, so I think that this is not surprising. I hope that you were all able to actually answer this item correctly. And what happened here is that you were using your relational conceptual understanding. You used the implicit information you already had about these food items to answer this question. And by the way, you overlooked the obvious explicit similarity that I tried to create with the apple and the cucumber. So you know how this works, and we should get a bit more serious now and try this again with a chemistry example. So you ready? Here comes the question. Which two nucleophiles would react similar with this brome alkane in a substitution reaction? This is a bit more complicated, and Michael will pull up the poll, just maybe a couple of seconds. Yeah, okay, so that everybody can see the structures. Oh, I see in the chat everybody is debating if the cucumber has not just more sugar than the apple. But we can maybe save that question for the panel later. Okay, everybody has made their choice. You see, Michael can close the poll. You see here that, I mean, most of you have chosen A and B, which is the correct answer, but there are also some in the audience that were not quite sure about this answer here. So what you see here is that A and B are good nucleophiles, whereas the carboxylate in C profits from resonance, and thus it doesn't have a localized charge to be a good nucleophile. So to illustrate you again the idea of this item design with our fruit analogy, you see here again that A and B is our apple and our banana because they have the most sugar in it, and also A and B are the two good nucleophiles here. And yeah, so this was the idea of the item design, and then we went ahead for our study and we designed items to decide between SN1 and SN2 reaction in these 4 concept categories. So we had nucleophilicity, hyperconjugative effects, solvent effects, and leaving group. And the general prompt was always indicate the 2 structures that would react similar in a substitution reaction. And we also did some interviews and piloting before using the items, just to ensure that students are understanding the prompts and the item correctly. I will quickly walk you through the study design. So we had 2 leading questions. One was, how do students actually judge a comparable reactivity in items that are explicitly distracting? And how does students' level of elaboration, when asked to provide a reason for their choice, relate back to their performance? So is there, does an elaboration prompt change their performance or change the rate? It was an exploratory quantitative study with a bit of a qualitative part, and I have to say, I have to emphasize that it was exploratory, because there are still so many questions that we need to answer here, and there's a lot of research that needs to be done to actually dig deeper into the topic. So we had 156 students, chemistry major, and student teachers at the end of their first year organic chemistry course. And our instrument consisted of a paper pencil test. Part 1 was just the multiple choice items that you've seen on the slide before, and part 2 was the same multiple choice items. I mean, you mixed it a little bit around and in elaboration prompt. So the instrument consisted of 68 items in total, and we had these 4 concept categories that I've shown you all as well on the slide before. And then we did the analysis, the statistical analysis, and we looked for a rubric, how we could code students' elaboration. But before we go into the statistical analysis, I want you to show how we did the rubric for coding students' elaboration. Here you can see on the left-hand side the item for, or an item of the concept category leaving group. And on the right-hand side, students' answers for choosing A and C. So those students who got that item correctly. And I want you to think about which answer would you rate as more elaborated than the others when you had to estimate students' understanding. And I have to ask Michael to set up the poll so that, I mean, Michael, have you the answers, the student answers in the poll, or should we give some? Oh, yeah, okay, perfect. Okay, I think we can close the poll. Everybody has made their choice. So C was the student answer that most of you rated as much more elaborated than the rest of it. And that's quite good to see that, because this is also the category that we coded as the most elaborated in our students' answers. One thing I have to say, if you plan a paper pencil test in such a way and you have students elaborate on an answer in a very limited way, it's sometimes hard when students don't have enough time to actually elaborate, or maybe the situation in which you do the paper pencil test does not engage them actually to reflect a lot on their reasoning. It's hard to use a very in-depth qualitative coding afterwards. So this is why we couldn't use also maybe established codings that have used in interviews, for example, and we had to look for another rubric that would capture the students' elaboration answers here. It's always a balance between what you want to achieve with your paper pencil test, and in our case, we needed to test a higher number of items for the sake of depth in students' answers. So it's always a balance between what is your goal and what does it mean for the time and maybe frustration of the students if they have to answer too many items at once. So I'll show you how we proceeded with the rubric. Based on our item design that we wanted to use, we focused on explicit and implicit features. So this was kind of an obvious code that we wanted to use as one dimension. So do students actually mention explicit properties or explicit features and that they see in the structure, or do students able to infer an implicit property such as electronegativity? And then we thought, okay, we're giving them a context, a reaction type, a substitution reaction. So we wanted to differentiate between those who were just picking up a feature or those who were more connecting to the reaction type or to the problem context that we gave them. So these are the four rubrics or the four elaboration code that we use to code students' answers. So let's have a look at our first results when we just looked how students did on all the concept categories and on the items, and you see that's been difficult because you can see that the items were answered quite differently. So students had no problems with the items in the category solvent effect, but they struggled a lot in the category nuclear felicity. And we thought, but we have designed the items kind of similar from the beginning. And we had, because of this result, we had to, of course, run a factor analysis to see if they actually load on the same factor or not. And what we see is that we could determine that some subscales that we tried to create for leaving group and for hyperconjugative effects, for example, are loading on a separate factor. So what we would call then item type 1, though, these are all the items in the subscales that the factor analysis determined as loading on item type 1, and other items that seems to load on another factor. So when you have such a result that we got from the beginning and you run a factor analysis that shows you a bit different picture than what you expected from the beginning, you need to have a closer look at the items to find hints what's actually going on here. So we went back to our items and had to reorganize the items in the subscales. And we found that while we thought from the beginning that, for example, this item on the left-hand side should be distracting, but it was not distracting for the students because they were just looking at the two halogens and not at the alkyl chain that we wanted to, that we thought is distracting for the students. I mean, you're always more clever at the end of a study, and you look at your decisions that you made and you're like, why haven't I thought about this before? But this is what happened. So a lot of the items who were loading on factor 1 have some sort of explicit features that support students in their item solution. And all the other items that were loading on factor 2 have no explicit feature that would support the item solution. So here in the nuclear felicity item, you can see the negatively charged oxygen, which is quite distracting the students. So they often picked A and C in this item. So, but I guess there's much more further research needed to actually finally determine how students are actually perceiving these items and what are features that are much more relevant or not relevant for them. So after our reorganization of the items, we looked again at the box plots, and you can see there's a large difference between item type 1 and item type 2. And students did far worse in items that did not support the answer on the surface level. But I was actually surprised to see such a large difference between the two item types. And this also calls us for attention when designing tasks in organic chemistry, because when we know that students tend to use surface features to make their decision and to make their answers, So we have to take this into account when designing our items. We see a small effect size as well for the elaboration prompt between part 1 of the instrument and part 2 of the paper pencil test. The small effect size of the elaboration prompt could either indicate that the items were quite too difficult for them, so that even an elaboration prompt would not have engaged them to think more in depth about the item, or it could be that just the prompt and the amount of items that we might give them that we have gave them in the test might not engage them to reason on a deeper way. Okay, so that is the statistics, the box plots for the 2 different item types. And now let's have a look at students' elaboration. And here I'll walk you through this diagram. So one color represents one elaboration code. So the dark blue, for instance, represents the percentage of students who received an E1 code and choose the correct answer. And the shaded dark blue part represents those students who had the E1 code but answered the item incorrectly. Overall, students' elaboration, you could see that most of the students were using an explicit elaboration. So they were mentioning explicit features of structural representation that we gave them in the items. But you can also see that some students were able to elaborate on an implicit functional level when providing reasoning for their choices. What this diagram shows us is that students who use a more explicit focused elaboration have a high chance of solving the items of type 2 incorrectly. This would mean that I don't even need students' final choice in the multiple choice item, because how they would justify their choice would already indicate how they would perform in the item. So when looking at the higher codes, the orange and the yellow ones, you can see that the percentage of solving both item types 1 and 2 incorrectly decreases. So the more the students are able to reflect on implicit properties and function of entities while solving the items, this leads to a higher chance of success. I mean, the findings that students have a higher chance of success in organic chemistry when including implicit properties or some sort of mechanistic reasoning in their elaboration is not surprising, and it also confirms results from other studies, such as Melissa Weinrich's and Hannah Savian's work on abstraction, Alison Flynn's work, and it shows how important it is to spend much more time in instruction on linking representations with conceptual understanding. But it also points out that besides using multiple choice question in assessments, it is quite important to also include students' reasoning in the assessment as an additional resource to estimate their understanding, especially when items could not be designed in such a clear way as we try to do that. So where can we go from here? So we've seen that assessing students' understanding can be quite misleading when the correct solution is possible based on surface features, and that we have to combine our assessment with students' deeper reasoning. And for example, and Trigas had published about this in the 80s, maybe using 2-tier multiple choice question to dig a little bit deeper and try to assess the reasoning process, and just instead of just the product of a factual question. But supporting students to use their conceptual knowledge and to activate a deeper conceptual reasoning does not come deliberately, and it already starts during instruction. So when we want to assess students on a deeper reasoning, then we need to include this as well into our teaching and into our instruction before we assess them. And I'm pretty sure that a lot of you in the audience are pretty aware of this issue and try to incorporate opportunities in your teaching to help students become aware and reflect about their intuitive approaches. And as we have this unique situation, having you all here and I want you to think about your experiences in teaching. So what are you doing in your teaching, in your instruction, to support students to be more reflective and to become aware of how they approach problems and yeah. And we do now a breakout. And I will leave you with this question a bit. We do an adapted version of what Gwen used, what Gwen was talking about on the first MISA conference. I think she called it a think, pair, a think, collaborate chat. So we do a think breakout chat. In the breakout, I want you to get to know each other and exchange your experiences. What have you done in teaching, and to exchange your ideas. And then you already practiced this in Ginger's talk. In your group, decide if you have an idea or if you have a question that you want to share as a group via the chat box. And then afterwards, we resume this. Okay, think, chat, learn. This was Gwen's think per chair version. So Michael, you can pull up the breakouts, and Julia had already posted the leading question in the chat, so you should be ready.
Oh, the breakout rooms are open. People should be able to join them now.
That's so interesting, Nicole.
Thank you.
Really great.
I'm just freaking nervous. I should close the chat because that is so distracting.
Yeah, I know it is distracting, but try not to. So I've been very positive.
I hope so. Oh yeah, the factor analysis. This is something that normally comes comes up.
So if people are in the main room and want to join their breakout room, they can just click on either the accept invitation or click on the breakout rooms at the bottom of the screen and then join.
So how many minutes do we have left, Ashen?
Well, going by my watch, I think we have about 2 or 3 minutes.
2 or 3, okay.
So if we want to give them another 2 minutes in the breakout rooms, and we'll call them back. And if you want to wrap it up, then
yeah, I have 1, 2 slides before I finish. I might need 3 minutes.
Okay, that's okay.
That will be fine. Huh?
That's fine. So perhaps in a couple of maybe in a minute or so, Michael, you can tell the chat groups that they've got 60 seconds left.
Sure. Yeah.
Yeah, the poll took quite longer than I expected.
Cool, thanks, Michael. So all right.
Michael, can you tell the breakout rooms that they have to, when they have something to share, that they can already start to type in the chat?
So also they won't be able to type in the main chat bit. So when they come back.
Okay, perfect. Yeah. Okay.
Breakout rooms are a bit weird. It's like going into a different building and then. All right, shall we say a minute?
Yep.
So it'll be 60 seconds and then I'll give you a shout when everybody's back in.
Mm-hmm. Is everybody back?
So another 24 seconds. A minute is a long time when you're waiting. I've just realized, Nicole, for your talk, I should have put just this von Liebig's lab as my background rather than.
Yeah, I know.
Missed opportunity. All right, so that should be everybody coming back in now.
Okay, when everybody's back, just if you have an idea or if you want to share what you've were discussing in your breakout rooms, feel free to type in the chat. I think just to share what you experienced in your teaching already. So that would be cool. So about reflecting about their implicit assumption, just making it quite transparent for them. Answering questions such as how and why to help students think about phenomena. Oh, I just can't keep up with all the things that are coming in the chat. That's brilliant. Make different choices, validate their instinct. They're just going through it. Scaffolding, strategies for surface reasoning. Okay, wow. I mean, Michael, we're saving the chat so that I can go over it later. I want to quickly resume the talk for today by just briefly mentioning a teaching strategy that's been used widely to actually help students to make the unconscious conscious. And you can also call this kind of a metacognitive loop. And in the middle, you can see a lot of some work that's been done and research that's been done that already used this idea of that metacognitive loop. So the idea is that when students have a prompt, they can just go ahead and do their first attempt and answer a prompt, and then they're provided with some type of instructional input. This could be, as in Talanka's work, to prompt them to reflect on students who got this item or the prompt incorrectly, which changed their performance. Or you can also use like conflicting animations, such as Risa has talked about earlier and on the MISA conference. Or you can give them worked examples such as expert or peer solution, or have them analyze written work from peers, such as Ginger is using in her Writing to Learn project. And there's also work from Elizabeth Juriev, who had done this. And then after this instructional input, to go ahead and let students revise their initial attempt and their initial answer. In short, so that students are able to, so that we're not expecting the students right away to use all their resources that they have to actually apply them all the time. It gives them the opportunity in a, I would say, in a safer way to practice and to build on what they could do in their first attempt. And the one thing is that we can create a lot of learning opportunities, such as this one. But as ChemEd researcher, we also need to look into evidences that such instruction actually works the way we intended. So there are plenty of questions that need to be answered to inform future teaching, such as how can we determine changes if we use these type of instructions? What can be taken as evidences here? Do changes last when we do something differently in our teaching? How can I observe this? And how can students actually use knowledge pieces or resources in another context? And when they do, what are they doing actually? So these are a lot of questions that would need or would call us for further research. And I hope some of you feel inspired by the fabulous talks here at MISA to answer some of these pending questions to build an evidence-based foundation for teaching practices. And just a quick overview, I have to really thank Michael and Ashlyn for this conference and just being fabulous, and also this open and respectful chemistry education community and everyone here today participating, brainstorming with us. And you can see them on the right hand side. This is just my fantastic chemistry education research group in Gießen. And last sentence, for all of you who are new in the field and want to start research, reach out to us, to everyone here, and establish collaborations. And thank you very much for being here today.
Thank you so much, Nicole. That was really amazing, both insightful from a methodological point of view on exploring student reasoning, but also very insightful on the actual nature of student reasoning and the considerations that we need to be making when it comes to designing our prompts and questions. So thank you very much for that, Nicole. So if you can stop sharing your screen, I'm going to move on, and I'll just introduce our next speaker, which is the amazing Ryan Stowe. So Ryan is at Wisconsin at the moment. Ryan and I both met when we were postdocing in Melanie Cooper Group's in Michigan State, and I believe Melanie is on the call, so hello to you, Melanie. Ryan is interested in advancing, I suppose, beyond the deficit model that does kind of characterize the types of things that kids can do, towards creating environments that will really help them to use what they know to make sense of the world around them. So today, Ryan is going to be sharing some thoughts on cognition and its role in assessment, which chimes really nicely following on from Nicole's wonderful presentation. So Ryan, I'm going to stop sharing and I'm going to ask you to share your